Now I want to talk about something that's commonly called a related rate. And the idea behind related rates is that if you have an equation that is static in its nature, by that I mean it tells you how things are related when nothing's moving, nothing's changing, then that equation can be used through calculus. It can be altered so that it can be used when you are in a situation when things are in a state of change instead of in a static and unchanging state. For example, let's say we had a balloon that's spherical in its shape, and we would know that from geometry class that the volume of that balloon is going to be 4/3 pi r cubed. So what that equation tells you is that if nothing's moving, if nothing is being altered, if nothing is changing, that's how volume and radius are related to each other. All right? But what if things are changing? So what if we knew that air is being pumped into the balloon at a rate of 100 cubic centimeters per second? All right, if you know that air is being pumped into the balloon at that rate, then what you know is that volume, and we know that it's volume that's changing because cubic centimeters is a measurement of volume, and it's changing per second. So we know that this is a dV dt because there's a rate of change of volume on top over a rate of change of time. So if you know that air is being pumped into a balloon at 100 cubic centimeters per second, then what you know is dV dt, rate of change of volume with respect to time. And if you were being asked what is the rate of change, what is the rate of increase of the radius of this balloon, how is the radius changing? Then that means that dr dt is what's being asked for. So let's say that we did want to know how is the radius changing at the instant that the that the diameter is equal to 50 centimeters. So again, volume is changing at 100 cubic centimeters per second. They want to know what's happening to the radius. How's the radius changing the instant the diameter is 50 centimeters? Well, if the diameter is 50, that makes the radius 25. And what I can do is take this static equation, meaning nothing's moving, nothing's changing, and turn it into, through the use of calculus, a related rate type situation. So I take the derivative, and the way you should look at it is volume is no longer a constant or a variable, all right? R is not really a constant or a variable. They're both functions of time. So my equation goes from being V equal 4/3 pi r cubed to volume as a function of time equaling 4/3 pi times radius as a function of time cubed. Now you don't actually have to write it out like that, but at least in your head you should see that that's what's happening. This has gone from a static to a dynamic. Things have gone from sitting still to changing. So differentiating with respect to time, dV dt will equal to 4/3 pi. Using the power rule, 3 comes down, r of t drops to the second power, and then chain rule says times dr dt. Cleaning this up just a little bit, this becomes dV dt equaling the 3's cancel there, 4 pi r squared dr dt. I'm going to just drop the of t notation for the moment. And then dv dt, which is 100, will equal to 4 pi times the r. And what they're wanting is to know what is happening to the rate of change of radius at one instant, at one moment in time. They don't tell you when it is, and that's why I took the t out, because they're not going to tell us a time, but they did tell us what it was at whatever time that is, and it is 25. And then there's the dr dt that they actually want. So, cleaning the numbers up just a little bit, 25 squared is a 625 times a 4 is 2500. So this is a 100 equaling 2500 pi times dr dt. So dr dt is a 100 over a 2500 with the pi. Remember that pi has to be on the bottom because you divided by it. All right. And reducing the fraction, that's a 1 over 25 pi. Now that is the exact answer. That is precise, that's perfect. All right. If you choose to turn that into a decimal, if that's just what is more appealing to you, remember your calculator has pi built in above the caret key. So you go 1 divided by 25 pi would be a 0.0127 if you wanted to carry it out to 4 decimal places. And what would your units be? Well, since it's a dr and radius was measured in centimeters, it would be centimeters per, and the t here, time was being measured in seconds, so it'd be in centimeters per second. All right, it would match up with the units that you had been using all along. So again, what we're able to do is take a static and turn it into something dynamic through the use, static becomes dynamic through the use of derivatives. All right, so let's try that again. There's a couple other tricks, techniques, whatever you want to call them, that you need to see. All right, let's say we have a water tank that's in the shape of basically a cone, an ice cream cone, a snow cone, or something like that. Circular at the top, coming down to a point. All right, so it's in the shape of a snow cone or an ice cream cone with a base radius of 2 meters. And when they say base, it doesn't mean it's sitting upon it. It means it's 2 meters right there. And a height of 4, which means outside distance out here is 4 meters, or that would be the same distance if you were to draw it in here. Okay, so what we have is something, basically, if you look at half of this cone, we sort of have a triangular arrangement here. And it says the water is being pumped into the tank at a rate of 2 cubic meters per minute. So that means, since it's 2 cubic meters per minute, if you just look at your units, that's got to be a dV, because this is how volume's changing, over a dt, because this is how time is changing. That's what has to be given to you. It wants to know the rate at which the water level is changing at some instant, all right? At some instant when it's 3 meters deep. So what that means, I'm going to redraw this thing. So here's your entire cone. At some point in time, the water is going to be down here at 3 meters deep. Right? At some point in time, that's going to happen. And if we call this arbitrary distance right here height, then what they're wanting is the dH dt. Again, you have to know the static to ever be able to figure out the dynamic. And the static says that the volume of a cone is 1/3 pi r squared h. Now, the problem with this one, in comparison to the last, there's a problem we have here, and that is we've got too many variables here. All right, right now, when we take a differential, when we do a derivative, we can't have multiple variables floating around like this. All right, we can't have an r and an h in here at the same time. All right, we don't know how to take the derivative of that at this point in time, because the chain rule we've seen is only a part of the real, true, the full chain rule, and we can't do that kind of derivative yet. So what is used in this type of situation, most commonly used, is going to be proportional triangles. So remember I said there's sort of a triangle going on here. Let's draw it. We have a triangle here. If you look at the full size tank, it's a 4 by 2. All right. The water's not all the way to the top. So the triangle that exists here, all right, is an H by R. And if you look at the height of the water and the radius of the water, that's what's going on. You have an H by R triangle inside of this larger triangle. So what we can do is set up a proportionality. Since these two triangles came out of the same physical object, they are in proportion. So we can say 2:4 as R is to H. So I can cross multiply. I get 2H equals 4R. What I have to do is decide, what do I actually want to solve for? Do I want to solve for R, or do I want to solve for H? Because I could do either one. I could say one alternative, if I divide by 2, is that H equals 2R. Or my other choice would be to say R equals a half of H. Which one do we want? Which way do we want to go? Well, they've asked us, how fast is the water level rising at some point in time? In other words, we've already said it's dH dt that we want, which means H needs to stay in the problem, and R is the one that needs to be replaced. That's how I decide that this is the one I want to use. R's got to go. All right, so I'll go back to the original static version of the equation, and I would remove R and replace it with 1/2 H. Again, because I need to keep H in the problem, because it's something I need to work with in my final answer. So my volume now, I'm going to clean this up now. 1/3 pi times squaring a half gives a 4th. Squaring H gives an H squared. There's the H that was already there. Cleaning up a little bit more. There's the volume formula for this specific cone-shaped water tank. All right, so now I can figure out how things are related. I can take the derivative of volume with respect to time, and that's going to be the 1/12 pi. The 3 comes down, power gets reduced, chain rule gives us the dH dt. All right, so at this point I could clean up a little bit more. 3 and a 1/12 is a 4th. Okay, there's the H squared and the dH dt, and now I'm going to start plugging in everything I've got. For dV dt, it's a 2. And then it said in the problem, find the water level when it's 3 deep. That's what we want to see. All right, so 2 equals 9/4 pi dH dt multiplying by a reciprocal dH dt, then would be an 8/9 pi. Okay, 8/9 pi is, again, an exact answer. If you feel inclined to plug that into a calculator, be my guest. But again, I've taken a static relationship used proportional triangles to reduce it down to no more than one input variable, and then used derivatives to tell how the static equation turns into a dynamic and things start to change and things start to move. Right? Lots of problems in the book like this. There's another one I wanted to look at that deals with a swimming pool. It has a unique shape to it. We're going to try and recreate that drawing. It says a swimming pool is 20 feet wide. And this I'm going to write down because in my two-dimensional drawing of this three-dimensional pool, you will not be able to see the width. Okay, so I'm writing that down. So the pool roughly looks like this. Has a vertical part here, angled, flat bottom, less angled, horizontal part, and then an upright. Okay. Not the best artist in the world, but you get the idea. All right, so this right here is 3 feet. So is this, right? And then the next section all the way to the bottom is 6 feet. So this pool is at its deepest point 9 feet deep. Okay, from top to bottom, 9 feet deep. And these sections have individual measurements. From here to here is 6. From there to there, flat part is 12. From here to there is an additional 16, and then a final 6. So if you add all that together, you see that the pool is a grand total of 40 feet long, right? So here's what they tell us. A swimming pool that is 20 feet wide, again, wrote that down, 40 feet long, which is what you get when you add all those together, 9 feet deep, at its deepest point, which is the 3 and the 6, and 3 foot deep at its shallowest point, which would be, shallowest point would be up here. If you were standing right here, you'd be at the shallowest part of the pool. And it says the pool is being filled at a rate of 0.8 cubic meters per minute. So 0.8 cubic meters per minute, I do not think can be confused with anything but a dV dt. Here's how the volume is changing over time. It wants to know how fast is the water level rising. So if the water, was in here at some level, how fast is it rising? So if you want to let depth of water be marked by a capital D, then rate of change of depth with respect to time is what they want to know. And they want to know how fast is it changing when it is 5 feet deep. All right. So what that tells us when we look at that 5 feet deep is they've given us a lot more information on this pool than what we really need, because this is 6 feet over here. So the water is below this level here and there. So none of that and none of that actually matter. Okay, I could redraw this pool in a slightly simplified fashion. This part, and then that part is all I really need. Okay, that's all I really need. So again, this part is 6 feet. This part is 12 feet. And this part from here to its end is another 16 feet. All right, the last 6 feet of the pool, which was up here, doesn't even matter because the water is not there. It has not reached that point. Okay, because I know that from up to this point here, it's only 6 feet. So from here to there is 6 feet. And we're only looking at a 5-foot depth. All right, so I need to know when the water is any depth D, at any depth D, because I've chosen D to mean depth, well, how much water is in my pool? Okay, how much water do I have when the water is D, at a depth of D? All right, I need to find a volume formula. And I'm going to do it by breaking this pool down into 3 pieces. All right, 2 of them are triangles. 1 of them is a rectangle, at least on the cross section they are. My artwork is horrible, but you get the idea. All right, let's do the easy one first. Let's go for the middle. All right, this rectangle in the middle is 12 by D by 20. And again, the 20 is the part you can't see. That's the 3-dimensional part. So the volume of the water in this pool at any point in time is going to be a 20 by 12 by D for the part in the middle, and only for the part in the middle. All right, so for the left-hand side, I'm going to look at proportional triangles again. Triangle from the left-hand side measures 6 by 6 if the pool was full. So what we see is here a 1-to-1 proportionality. Okay, a 1-to-1 proportionality. So if the water was at depth D, we'll look at the smaller version of the triangle here. The depth D, the width here would be D. It's a 1-to-1 proportionality. So for the area, okay, the area for a triangle is 1/2 the base times the height times, we have to multiply it by the 20 to get the 3-dimensional. All right. Now on the other triangle looks like this. The triangle on the far right-hand side measures a 16 by 6 if it were full, but it's not full. Okay, the water is only up at depth D right here. So I'm going to pull off, and I'm going to do proportional triangles on that as well. Okay, if I look at that in the form of a proportional triangle, again, what I need to figure out is how much area I have. Oh, wait a minute. I pulled off the wrong piece of the triangle. Let me back up. I pulled off the outside of the pool instead of the inside of the pool. Forgive me. All right. Again, the smaller triangle was for this portion of the pool up here. I was looking out here. Need to be in here. That's the part that actually holds water. That's the part I need. Right, so let me try that again. Have my triangle upside down, basically. All right, this triangle, when it's got water in it, if it were full, would be 16 up here and 6 there. Again, I had it upside down. Apologize. The triangle with water is down here. Okay. All right, pulling that smaller one out. The D here, and some sort of width here. We'll call it a W. All right, again, 16 is to 6 as W is to D. And it's that W I need, so W equals D times, and 16 over 6 reduces to an 8/3. It's an 8D over 3. All right, so this width right here is an 8D over 3. All right, so when I add that to my volume equation, what's the volume of this triangle going to be? Well, it's 1/2 times the base, which I've called W, which is an 8D over 3, times the height, which is D. All right, that's an area formula. Multiply it now by 20 to turn it into a volume. All right, all this needs cleaning up. All this needs some cleaning up. The volume formula, as I clean it up, I'm going to multiply the 20 by the 12. That's a 240D. plus half times 20 is a 10 and a d squared, plus a half times the 20 times the 8/3 is an 80 over 3 d squared. And I can take an 80 over 3 d squared and add a 10 to it. And I get my volume equaling 240d plus 110 over 3 d squared. All right, so that's a volume formula. That tells me the volume of water in this pool when the water is at any arbitrary depth up to 6 feet. And we're going to be at 5. All right, so that's the static equation for the volume of water in this pool. Therefore, dV dt would be equal to 240 rate of change of depth with time plus 110 over 3, 2 comes down, d goes to the first power, and the d of large D dt comes in again. All right, and this large d dt is what we're looking for. So what you would do at this point, I'm about to run out of paper, so I might leave it for you to finish. You plug in the dV dt, which was a 0.8. Then you plug in the D, and they want to know when it was at 5. And all you have to do is solve for the rate of change of depth with respect to time in this equation. And that is all they need to know.